Hello, and welcome to another episode of Science on the Edge. I'm Dr. Mike Darcy, and in today's episode, we're going to be talking about AI. Now, before we get started, if anyone would like to follow me on Twitter, my Twitter handle is @MarkOfTheD. That's at MarkOfthed. Okay, so let's get started. AI, artificial intelligence. I'm going to talk about different categories of AI. I'm going to then focus on the AI that's in the news right now, GPT. I'll discuss how it works, its uses, and its limitations. So let's get started. So, AI, NLPs, and GPT. So let's start with some definitions. First of all, the terms artificial intelligence, machine learning, and deep learning represent a sort of nested set of disciplines, each a subset of the former. This illustrates an evolution of capability and focus within the broader domain of computer science. Basically, you can imagine these three sort of categories as layers of an onion when it comes to artificial intelligence. So basically, AI is the broadest category. Machine learning is sort of a more focused subcategory, and deep learning is the core. So let's start with a general definition of artificial intelligence. So the broadest term that encompasses the development of computer systems to perform tasks that normally require human intelligence is AI. So AI basically does something that would normally be done by a human. So its purpose is to perform a task, some sort of behavior, some sort of function that normally would be performed by a human. These tasks include decision-making, visual perception, speech recognition, and translation between languages. AI systems can be rule-based or learning-based, and they may employ a variety of approaches, including both symbolic reasoning and statistical methods. Now let's zoom in a bit and look at machine learning, ML. ML is a subset of AI focused specifically on the idea that machines can learn from data. They can identify patterns and make decisions with minimal human intervention. It involves algorithms that improve automatically through experience and by the use of data, usually big data. Luckily, we have an internet, so we have a huge amount of data. These algorithms come in three main flavors: supervised learning, unsupervised learning, and reinforcement learning. Now let's zoom to the core, deep learning. Deep learning is a further specialization within the sphere of machine learning and involves neural networks with many layers, hence the term deep, that enable progressively higher levels of abstraction and understanding from data. These neural networks, particularly convolutional neural networks, CNNs, and recurrent neural networks, RNNs, both of which I will talk about shortly, have been pivotal in advancing fields like computer vision and natural language processing. Okay, now let's talk about some general categories of AI before we focus in on natural language software and GPT. So first of all, symbolic AI. This is also known as good old-fashioned AI or GOF AI. It operates on the principles of logic and rules. Basically, it utilizes if-then rules and decision trees to create deterministic outputs. Basically, you need a programmer to write every single instruction with symbolic AI. If this, then that. If this, then that. If this input, then that output. There's a certain limitation there because you can't really predict every single possibility. Not in advanced systems anyway. Yes, perhaps in a chess playing program you can. Even then it's a bit tricky. But as soon as you get to speech recognition, facial recognition, it becomes a little bit more complicated. And you can't really predict every eventuality. No people sound exactly the same. No two faces are exactly the same. An example of symbolic AI, expert systems that diagnose diseases based on a set of symptoms and rules. Then we have connectionist AI. This emulates the human brain's structure and function through artificial neural networks, ANNs. learns to perform tasks by considering examples, generally without task-specific programming. An example would be deep learning models used for image and speech recognition. Then evolutionary computation. Inspired by biological evolution, it employs algorithms based on mechanisms of evolution, like selection, mutation, and crossover. This optimizes problem solving by iteratively improving a population of candidate solutions. One example would be genetic algorithms used for optimizing the aerodynamic design of vehicles. Another example would be how we taught robots to walk on two legs. You might not realize this, but we spent about 60 or 70 years trying to program robots to walk on two legs, and every time they fell over. Because the problem is, really, with walking, it's extremely complicated and it's different every time. Now, we as humans, we're constantly making microscopic adjustments as we move around to stop ourselves from falling over. You can't program every one of those possibilities into a computer. So what we did instead was we used evolutionary computation. A bunch of programs were written to attempt to make a two-legged virtual creature on a computer screen walk across a surface, avoiding objects and not falling over. These programs were then run, and they all fell over, but at different times, at different points. The best candidates then were mutated. Randomly, their programs were changed, and a bunch more programs were generated from those. And they were allowed to walk along this virtual environment. Again, most fell over very quickly. At each stage, though, the candidates that walked the farthest, the most efficiently, they were kept, mutated, and the offspring allowed another try. Very rapidly, this approach resulted in virtual two-legged organisms that could walk across the screen without falling over and avoiding objects very efficiently. The software was then used on actual robots and improved upon. And now we're in a situation where we have two-legged robots that can walk, run upstairs, and even perform somersaults. That's the power of evolutionary computation. Next, Bayesian networks. Based on Bayesian statistics, they model the probabilistic relationships among variables, useful for inference, decision-making, and prediction when dealing with uncertainty. Example, spam filters in email services use Bayesian networks to classify messages. They get better at doing it as they go along. Fuzzy systems. Instead of binary true-false values, which is how a lot of AI systems used to work, and still do, it works with degrees of truth using fuzzy logic. Think of it as more of an analog approach than a 0-1 digital approach. This handles imprecise or noisy data effectively. An example, home thermostats that adjust temperature levels based on fuzzy rules rather than strict set points. Which brings me to hybrid AI systems, the best of more than one world. This combines two or more types of AI to leverage their strengths and mitigate their weaknesses. Example, neuro-fuzzy systems integrate neural networks, learning capabilities with fuzzy logics, handling of uncertain or imprecise data to get the best of both worlds. Then reinforcement learning. This models decision-making as a process of actions and rewards within an environment. The AI learns to make sequences of decisions by trial and error, maximizing some notion of cumulative reward, such as winning a complete computer game. Example, AlphaGo, the program that defeated the world champion in the board game Go. Natural language processing, NLPs. Now, natural language processing is basically what GPT is, which I'm going to delve into in depth pretty soon. But let's give the broad overview, because GPT isn't the only NLP system. So, NLP systems, a domain of AI focused on the interaction between computers and human language. It involves understanding, interpreting, and generating human languages in a way that is both meaningful and useful. Examples: GPT, generative pre-trained transformer. This model used for generating human-like text, and I'm sure we've all used this now. Delving into NLPs, such as GPT. NLP, or natural language processing, is a fascinating subset of artificial intelligence that deals with the intersection of computers and human natural language. It's a technology behind language translation services, virtual assistants, chatbots, and many other systems that interpret and respond to human language. The GPT, Generative Pre-trained Transformer series, including the latest iterations such as GPT-4, represent the cutting edge in this field. Now let's go into the mechanics of how GPT operates. Okay, so it all basically revolves around something called transformers. So let's talk about transformer architecture. GPT is based on this transformer architecture, which is a deep learning model introduced in the paper Attention is All You Need by Vasmani et al. In 2017. The core innovation of a transformer is the self-attention mechanism, which allows the model to weigh the significance of all parts of the input data differently, enhancing its ability to understand context. So let's delve into that a bit more. Self-attention enables a model to process a sentence by considering the association between all words in the sentence simultaneously rather than sequentially. So it's not like an autocomplete. It looks at everything that's already been said and reevaluates constantly. This allows for more complex understanding and generation of text, as the model can capture nuances, idiomatic phrases, and long-range dependencies in language. This requires pre-training and fine-tuning and a huge amount of data. GPT models undergo two major phases: pre-training and fine-tuning. In pre-training, the model is trained on a massive corpus of text data. It learns to predict the next word in a sentence by seeing many examples. For example, GPT has been shown the entire corpus from various scientific journals. It's been shown the entire of Wikipedia and a bunch of other databases too. It's analyzed them and looked for patterns and remembered those patterns. The fine-tuning phase adapts the pre-trained model to specific tasks by training it on a smaller task. So a subset of data, such as biology, law, engineering. Language modeling objective. During pre-training, GPT uses unsupervised learning with a language modeling objective. This means the model aims to maximize the likelihood of predicting the next word in a sequence of words, thereby learning the probability distribution of a language. This requires tokenization and embeddings. So the input text is first broken down into tokens. So what you write as a question or an instruction is broken into tokens using a tokenizer. These tokens can be words or subwords. For example, ing at the end of a word. Each token is then transformed into a numerical representation or embedding, which captures semantic and synaptic meanings. So a number is generated with a weighting for each token. Layered architecture. GPT models consist of multiple layers of transformers stacked on top of each other. Each layer's output is fed into the next, allowing the model to learn increasingly complex patterns. This, for example, is how the human brain works in, for example, vision. When light hits the photoreceptors on your retina, this generates electrical impulses which go down the optic nerves. And at the first layer of the occipital lobe, which is at the back of the brain, this is where vision is located, there is literally just a one-to-one mapping of each photoreceptor. That would be layer one, equivalent to layer one of the transformer network. But then information from layer one is passed on to layer two, where patterns can be discerned. And then from layer two to layer three, where more complex patterns can be discerned, and then to 4, 5, 6. So you start off with just a bunch of pixels, then you get color, you get shape, you get movement. This is very, very similar to how transformer networks understand language. They start off with these basic inputs, and through tokenization, and movement of information from one transformer layer to the next, you get more and more complexity and more readability. Training scale. The models are trained on vast amounts of data and require significant computational resources, often involving hundreds of GPUs or TPUs. Now, this is why you need a lot of server space, some quite high-powered networks to run something like GPT, at least at the moment. Applications. After training, GPT models can generate coherent and contextually relevant text, passages, answer questions, summarize text, translate languages, and perform a variety of other language tasks, just using this transformer network based on tokenization and big data. So when it comes to tokenization, the process involves dividing text into a list of tokens. So this can be as simple as splitting by spaces and punctuation for languages like English, but can be more complex for languages without clear word boundaries like Chinese. Tokens as words and subwords. So tokens may be whole words, but they can also be subwords or sequences of characters that provide a balance between the flexibility of character level models and the efficiency of word level models. Subword tokenization allows the model to handle rare or unknown words by breaking them down into smaller pieces that it has seen before. When it comes to vocabulary and embeddings, each unique token corresponds to an entry in the model's vocabulary. The model assigns an embedding to each token, which is a high-dimensional vector that encodes the token's semantic and syntactic properties. Now, this can only happen because of the model training. Model training is so important. Tokens are used during both pre-training and fine-tuning phases of the model. The model learns the probability distribution of language at the token level, predicting what token comes next in a sequence during training. Handling of context. In transformer models like GPT, self-attention mechanisms allow each token to be evaluated in the context of all other tokens in a sequence, leading to a contextual understanding of language, which is very important. In terms of efficiency and comprehension, by using subwords, the model can efficiently process text with a limited vocabulary size while still comprehending a vast lexicon, including neologisms and specialized jargon, which all depends really on having a big training database and also the tokenization. So even if it hasn't seen a word before, it can kind of predict its meaning. Special tokens. Models often use special tokens for specific purposes, such as denoting the beginning and end of a sentence or a paragraph, or separating sentences from each other. Otherwise, you just get a big, meaningless block of text. There are limitations of current AI models, though. They're very good. As you know, they can basically give you some very convincing answers to your questions. They can write convincing pieces of text. They pretty much always sound accurate, although actually GPT can hallucinate sometimes and just give you information that looks accurate but really isn't. There are many limitations of current AI models. The current AI models, particularly those like the GPT series, have made remarkable strides in mimicking certain aspects of human intelligence. However, they do face significant limitations. First of all, data dependency. AI models require vast amounts of data to learn and make accurate predictions. The quality of the data directly affects the model's performance, and the models can inherit biases present in the data. One increasingly worrisome possibility relating to this is the fact that people are now writing documents and producing content that they place on the internet that has been generated by GPT. And if GPT then uses this data to basically, to train on in future versions, then it's going to be training on its own data, which could amplify inaccuracies. Time will tell on that one. Lack of understanding. AI lacks true understanding or consciousness. It processes data and identifies patterns, but does not comprehend the meaning in the way humans do, despite what some people say. You probably all heard of the Google employee who basically went to the press when GPT came out and said that he believed it was conscious. I believe he was immediately put on leave by Google. It's not conscious. Seems highly unlikely anyway. Not this version anyway. Future versions, though, may be different. This is evident in NLP models that can generate plausible sentences, but can also produce nonsensical outputs that a human would immediately recognize as such. Generalization. While models like GPT can generalize well across topics they've been trained on, they struggle with scenarios they haven't encountered before, or with tasks that require reasoning beyond pattern recognition. They basically go off what they've already been told. They're not creative. Basically, think about it in terms of physics. Now, before Newton, physics was pretty basic. The universe was understood in either biblical terms or ancient Greek Aristotelian kind of terms. But then Newton came around and changed the dynamics completely by inventing calculus and coming up with a totally new way of looking at the universe. Now, if GPT had been trained on pre-Newtonian physics, it could have never come up with Newtonian physics. It's just not that creative, at least not yet. Energy and computational costs. Training state-of-the-art models is resource intensive, requiring significant computational power and energy, which has financial and environmental implications. Although, as we all know, computers get faster and they get smaller, more powerful, more energy efficient as time progresses. So the computational and energy costs are likely to go down. Explainability. Many AI models, especially deep learning networks, are often considered black boxes because their decision-making processes are not fully transparent or interpretable. Basically, many of them rewrite their own software as they go along, meaning that very soon after their release, they are doing things, saying things, behaving in certain ways that no human programmed or can explain. Adaptability. Unlike humans, AI models are not inherently adaptable. They require retraining or fine-tuning to adjust to new tasks or changes in the data distribution. They're not as plastic as the human brain. Ethical and societal impact. AI can perpetuate and amplify biases present in training data, leading to fairness and ethical concerns. Additionally, the deployment of AI can have significant societal impacts, such as job displacement. Basically, Sam Altman, the CEO of OpenAI, who created GPT, has admitted as such. He's admitted that the job market is likely to be changed drastically by his creation. Not necessarily in a good way, by the way. There could be mass employment because of this sort of software. And if used by the wrong people in the wrong way to create things like tweets, websites, fake news, that kind of thing, elections, referendums, public opinion could be manipulated massively by AI, not necessarily for the better. Which leads me to artificial general intelligence, AGI. This is very important. We're not there yet. We have some pretty good AI, but artificial general intelligence is human level AI. So AGI refers to an AI that can understand, learn, and apply knowledge in a comprehensive manner akin to a human being. Current models are not capable of achieving this level of functionality. AGI requires not only wide-ranging knowledge across diverse domains, but also the ability to form abstract concepts, transfer knowledge between domains, and possess a form of consciousness or self-awareness. Current AI models, even advanced ones like GPT, are specialized and excel at the specific tasks they are designed or trained for. They do not possess, however, the broad, adaptable intelligence that characterizes AGI or human intelligence. The development of AGI remains a theoretical and aspirational goal, one that represents profound technical challenges and philosophical questions about the nature of intelligence and consciousness. I have no doubt that we're going to get AGI at some point, and that will change what it means to be human, what it means to be conscious, and could change the world drastically. May even make humans irrelevant, may make us obsolete. Time will tell on that one. Okay, thank you very much for watching. Once again, if you want to follow me on Twitter, my hashtag is @MarkofTheD. That's all for now, and I look forward to speaking with you all again very soon. Thanks again, and goodbye.